crack it. As promised in the previous video, we continue this series with Java 21 features. Today, we'll discuss one of the most important features, that's virtual threads. Why do we need virtual threads? What are its performance improvements? What was the problem in the platform threads and how that got fixed with the virtual threads? How to create the virtual threads? We'll see the coding examples for all these and let's start the discussion now. Before we deep dive into what virtual threads are and how it works, let us first try to understand the traditional way in which the thread works. So, threads is nothing but that is an instance of Java lang thread class, and we will call this as platform threads from now. Why are we calling it as platform threads? Because Java 21 introduced virtual threads as its finalized version. And since virtual threads is in picture, we have two threads now, platform threads and virtual threads. To differentiate this platform thread from the virtual thread, we will call this thread as platform threads from now on. So, what are these platform threads? Platform threads are nothing but the thin wrappers around the operating system threads. So, always there is a one-to-one correspondence between the Java threads and the kernel threads. What does that mean? When we create a platform thread, then that will directly corresponds to the kernel thread. So each platform thread will correspond to a kernel thread, and this system kernel is responsible for scheduling this Java threads. JVM is not responsible, but the system kernel is responsible for producing these Java threads. Also, creating these threads is really costly, and Java is using this thread pools to avoid the overhead in the creation of the threads. What was the issue with the platform threads? One of the commendable issue is scalability. Let's try to understand this with an example. So, I have an employee name and I want to query the employee object from the employee server. So these are the steps that are involved. First, I'll create a request. Why will I create a request? Anyways, in this microservices world, I'll call another service to fetch this employee object. So I have to format my request based on the service. So I'll create the request. Then I'll launch my request to the server or the network. Why? This will call the microservice which I want to call. Then next step, in the return response, I will unmarshal the object that is sent from the network to the format that I need. These are the three steps that I have been included in fetching the employee object with the employee name. So, when we consider all these, creating a request, this is an in-memory operation. Why? Because we are doing it in our memory. And unmarshalling the object, this is also an in-memory thing. But this launching the request in the server or the network, this is like a network operation. Why? Because I'll create a request and I will give that request to the network and I will wait for the network to respond to me with a response. So this is the request that is with the network and that is not with me. So if we consider these three steps, in this step my CPU will be 100%. Why? Because this is in memory. In unmarshalling the object, my CPU will be 100%. Why? Because this is in memory. But while launching the request to the server or network, my CPU does not have any work. Why? Because it launched it, it gave it to the network and it is just waiting for the network to respond. So by this time CPU is idle. On analyzing these three steps, this is a time consuming process, but in this time only the CPU is also idle. So how can we make the CPU more efficient? Let's think. So we can make the CPU more efficient by parallel processing. So we can make the CPU efficient by launching multiple requests in parallel. But as we know, the classical model is thread per request pattern, which is like how we saw here, like one JVM thread is associated with a one kernel thread. Since the platform thread is completely relied upon the kernel thread, this pattern limits the throughput of the server. Why? Because the number of concurrent requests is directly proportional to the number of threads, and that number of threads is directly proportional to the server's hardware performance. So this is a scalability issue. If we think by increasing the number of processes, even in that case, the number of available threads will be limited. So is this the only issue? No, this is not only the issue, but also latency is also a big concern. Let's understand why. So if we see here, we are trying to fetch the employee object from the employee server. Do we know that this will call only one microservices? No, there may be a chance that multiple microservices call will happen in this fetching only the employee object in this microservices world. So, while the application is waiting for the information from all the other servers that was involved, the current platform thread, the thread whichever calls this request should wait. In this way, latency is really a big concern. So, there's a lot of time wasted in the computation of the results. So, this is a major hurdle in achieving the high throughput for the applications. If you're not able to scale an application, there's a performance hit. We have latency issue. So, if we think how we can overcome these two, we will be thinking of the asynchronous applications. Platform threads has few issues with the reactive programming as well. Let's see what that was. So before we understand what it is, let's see what reactive programming is and how it solves the problem of latency. So whenever there is a request made to the asynchronous API will not wait for the response. Rather, they work on the callbacks. So let's consider thread T1 is calling the asynchronous API. During that call, the thread will move from the thread pool to the runnable threads. But will it wait in the runnable threads for the API's response? No, it will come to the thread pool. So suppose let's say the API returned response, what will happen? So this callback method will inform that the response is returned. So by the time the thread pool will again allocate some other thread in the thread pool to the API to handle the response. So in this way, multiple threads are involved in a single asynchronous request. So our latency issue is solved now using this asynchronous programming. Why? Because the threads is not now waiting in the runnable state for a very long time till the API response. Instead, it is coming back to the thread pool. But still we have the scalability issue. Why? Because the number of platform threads are still limited due to the hardware limitations. So another issue with this asynchronous programming is that multiple threads is involved in the single execution. So it is really hard to debug if something happens during the call. Also, for the asynchronous programming, we are using the loops and the conditional statements using the lambdas. So which will make the code even more complex. And we have to break our code into multiple smaller units. Why we have to break it into multiple smaller units? So that we can make it all asynchronous and we can make it to run independently. Is it that easy? No, it's not that easy with the new lambdas and the syntax of that. So why do we need virtual threads now? We would have understood by this time. Yes, we need virtual threads. Why? Because that will improve the code quality with a traditional syntax, with a sequential way, while having the benefits of this reactive program. Let's see how. What are virtual threads now? Like the traditional threads, virtual threads is also an instance of Java lang thread class, and that will also run its code on an underlying OS thread. Then what is the difference between the platform thread and the virtual thread? This OS thread will not block the OS thread for the code's entire lifetime, but platform thread does. We will understand this point with an animation in our next slide. So, the virtual threads are very lighter than the platform threads. We can create many virtual threads when compared to the platform threads because these are lightweighter. Also, we can create many virtual threads without depending on the platform threads. Why? Because in the platform threads, context switching is required, but with the virtual threads, context switching is not required. Why? These are just stored in the RAM. Also, with the virtual threads, we can call any number of blocking IO operation in parallel. How? These virtual threads are not blocking the OS threads. So we can call any number of blocking IO operations, which will make our CPU more efficient. Where will these virtual threads run? The virtual threads will be executed by this platform threads, but this virtual threads will not block the OS thread. Yes, we saw it right here, right? The virtual threads will not block the OS thread. Only one virtual thread can be mounted in the platform thread at a given time. Then how will the scalability be increased? Because previously platform thread was running, now virtual thread is running. What is the difference which makes the application scalable? Let's see This virtual thread is mounted in the platform thread, so it has its work to do, and the work of this virtual thread is calling an API. So suppose let's consider this virtual thread is calling an API, and during that time, will this virtual thread will wait for its response? Yes, it will wait for its response, but not staying in the platform thread, but it will get unmounted and it will go to the unmounted blocks of the virtual threads, and it will wait from here for the response to come. During that time, the platform thread will pick up another virtual thread from the unmounted ready virtual threads, and it will perform the execution that is assigned for this virtual thread. So what will happen to this virtual thread which was waiting for the API response? It will wait for the API response, and once the response comes, it will move to the unmounted ready virtual threads for it to get picked up from the platform thread. This is how the virtual threads increase the scalability. Previously, this platform thread was entirely blocked until the API response comes back, but now it's not the case. Yes, it is blocked, but not the platform thread, but the virtual thread. By the time the platform thread will pick up some other virtual thread and it will do its job. In this way, CPU's efficiency will also get increased. We have few other topics to cover, such as virtual thread spinning, differences between the virtual threads versus platform threads, creation of the virtual threads with coding example, performance improvements of the virtual threads. Since the video is long, we'll talk about this in the next section. Subscribe for more updates. Thanks for watching Crack It. Please do like, share and subscribe for latest updates.